I want to talk about the squeeze theorem. There's times when we're trying to find the limit of a function as x goes to a particular value, and it's really kind of tricky to figure out. But once in a while, we can compare it to other functions that are easier to calculate, and that tells us what the one we really want is. So here's the situation. Suppose I've got three functions, f, g, and h. And in some interval, I'm going to take the limit as x goes to a, right? So I'm going to look at, I really want to know what's the limit, where am I going here? What's the limit as x goes to a of g of x, right? Equals question mark, okay? Well, if it turns out that on some interval where a is in the middle of, somewhere inside the open interval, so a bunch of x values where this relationship is always true, where f is always less than g and that's always less than h, then the squeeze theorem says this: if the limit as x goes to a of f of x equals L, and the limit as x goes to a of h of x equals L, then the limit as x goes to a of g of x, whoops, what just happened here, of g of x is also equal to L. Right? If the small function and the big function are both going to a particular value L, then g, which is always sandwiched in between these two, it also has to be going to L. It gets squeezed right in there. I've actually, when I learned this was called the Sandwich Theorem. This book that we use calls it the Squeeze Theorem. The picture looks like this. If you've got some a value that you're approaching, and you've got some function, let's say this is y equals f of x, and I've got some other function here, let's do it in red, y equals h of x, and then we'll put something right in between red and blue. What's in between red and blue? Oh, maybe purple. And then I've got this other function that for at least some values of x here around a, g is going to be in between f and h, and if I can draw this better, it goes right up in through there. Right? So the thing is, as x goes to a, I'm looking at both f and h. I think I have my a in the wrong place here. Let me move this a over a little bit. Okay. Let's see if we can do this in, so a is about right here. And it looks like the L value is right there. As x approaches a, the function value f, the blue function is here at L, the red function is here at L, and what this theorem is saying is that the purple function in between will also be approaching L. That all of those functions go to the same point. If you know the bottom one and the top one go to L, then the middle one must go to L. As an example of this, I want to take a look at what is the limit as x goes to 0 of x squared times the sine of 1 over x. Now the sine of 1 over x was our example of the sufficiently squiggliness that could make a limit perhaps not exist. But what I want to do is I want to see this in a different light with the x squared out in front, and see that even though this is going to be really squiggly, the limit will still exist. Here's something that I know about the sine of anything. I don't care what you plug into the sine function, the output will always be somewhere between -1 and +1, right? And so, if I multiply everything by x squared, I've got x squared times the sine of 1 over x. 1 times x squared is x squared. -1 times x squared is minus x squared. And then I've got to decide, if I multiply everything by a number, does that keep the inequalities in the same direction or in the opposite direction? Well, I guess if you multiply by a positive number, the inequalities will stay pointed in the same direction. If you multiply by a negative number, it reverses the order. But x squared is a positive number. So what I have here is that x squared sine 1 over x is always in between negative x squared and positive x squared. Well, notice, if I look at the limit as x goes to 0 of negative x squared, well, there's none that goes wrong there. That's just your upside down parabola, right? As x is headed to 0, the y value is headed to 0. Likewise here, the limit as x goes to 0 of positive x squared, well, that's your right side up parabola. But as x is headed to 0, the y value is headed to 0. So what I see is that both this function and that function are headed to 0 as x goes to 0, and hence, by the squeeze theorem, the limit as x goes to 0 of x squared sine of 1 over x is also equal to 0. Okay, what I want to do now is I want to take a look at a picture of this thing. When I ask live math to calculate this limit, it does give me a value of 0. Graphically, what I see here is, let me change one color here. Let's change this to blue. And I want to make this black one thicker. All right. So what I have here is a red graph, which is the graph y equals x squared. The blue graph is y equals negative x squared. And the graph I'm actually interested in, the x squared sine of 1 over x, is this black graph that's going up and down in between them. There are infinitely many ups and downs. If I were to zoom in here, I would be able to see this thing going up and down, more and more and more and more. And so yes, there's this really, really squiggly, but the amplitude is being squeezed down to 0. So even though the function is vibrating faster and faster and faster as you go in, the amplitude of that vibration is going to 0, and the function value actually approaches 0. It's squeezed in between x squared and minus x squared. Okay, so there's times when we're going to use this. Actually, at some point next week, or maybe the following week, we'll look at sine x over x again, and use the squeeze rule to prove for certain that that limit is 1 as x goes to 0. But anyway, this is the squeeze theorem, and here's one example of how you'd use the squeeze theorem to prove a limit.